In this video, I want to talk about covalent bonds, how they are formed, and how you can use Lewis structures or Lewis dot diagrams to show a covalent bond. I want to start with just a little bit of review. Remember that chemical reactivity, or how an element reacts, is determined by the valence electrons of that element and the other elements that are involved in the chemical reaction. Elements react together to form compounds, whether we're talking about ionic compounds or covalent compounds. The reason they react is so that each atom in the compound will have access to 8 valence electrons. And we call this the octet rule because octet refers to 8. We talked about ionic bonds in a previous video, and they form when electrons actually move. They leave one atom, like we have the electron leaving the sodium and going over here to joining the chlorine atom. So it turns the sodium into a sodium ion with a positive charge and the chlorine into a chloride ion with a negative charge. The positive and negative charges then will hold the ionic compound together. We call this electromagnetic force or electrostatic force or electrovalent force. We see all three names, and basically it just means opposite charges attract, and positive and negative charges will attract each other. In ionic compounds, the chemical formulas that we have, such as NaCl, represent the simplest form of the element or the compound possible, and that's known as an empirical formula because, as I mentioned previously, this charge is present all the way around the atom, and so we can have other chlorines attaching. If there are other chlorine ions present, they'll attach or be attracted to that positive ion, and on the other side, if there are other sodium ions present, they'll be attracted to the chloride ion. So it just sort of builds up into what is known as a crystal lattice. So now we're going to move to covalent bonds, which are found in covalent compounds, which are made by two or more nonmetals bonding together. In covalent bonds, electrons are shared by atoms. There's a balance of attractive and repulsive forces forming this bond. The atoms are pulling, each of them are pulling on these electrons. The covalent bond allows each atom to have access to 8 valence electrons. Again, we still have this octet rule going on with covalent bonds. And the chemical formulas for covalent molecules represent a single molecule. They can be also known as the molecular formula. So unlike the ionic compounds and covalent compounds, you get a molecule that sort of stand alone. Covalent compounds have low boiling and melting points, and many common covalent compounds are gases at room temperature here on Earth. They typically are soft or brittle in the solid form, and they also do not conduct electricity particularly well, so they serve as insulators, not conductors. So how do we use the Lewis structure to draw covalent compounds, or even to figure out how a covalent compound must be put together? Well, first of all, you need to know that your covalent bond is formed by 2 electrons. One electron will come from the first atom, and the other electron will come from the second atom. So you're always going to have a sharing of electrons, one provided by one atom, one provided by the other. So we call these shared electrons shared pairs or bonding pairs because, of course, the 2 of them make the bond. Along with the shared paired or bonding pair, there'll be other electrons around those nonmetals because you're going to have an octet of valence electrons. So the ones that are not involved in the bond will be sitting there just paired up 2 electrons in an orbital like we heard about in our electron configuration. And those are known as lone pairs because they really only belong to their original atom of origin. When you're drawing a Lewis structure, your shared pairs are shown as a line, where the lone pairs are shown as dots, like we were doing with the ionic compounds. In covalent bonds, of course, or covalent compounds, you can have single bonds, where you just have 2 electrons, or double bonds, where it's like you have 2 single bonds, so there's 4 electrons involved, or even triple bonds, where you would have 6 electrons involved. We don't use square brackets or charges when we're doing covalent compounds with Lewis structure because, of course, they're not ions, so there are no charges present. The steps for drawing the Lewis structure starts with looking at what is the valence electrons of the atom. So you need to think about where does the electron fall, where does the atom fall on the periodic table, how many valence electrons originally are present, and then you can determine how many bonds are needed. So an easy way to think about that is if you draw a Lewis structure for that individual element, that individual atom, and there are parts of that Lewis diagram where there's only one electron present, it's not already paired up, where that single electron is found is a place where you could have a bond form. You want to look at the atoms involved in your compound and determine what's going to be your central atom. Everything's going to be around a particular atom or built out from one atom. Generally, the one that can make lots of bonds or needs to make lots of bonds is a good choice for your central atom. If you find that you have fewer atoms available than bonds, just going on a one-to-one relationship, you probably are going to have to put in a double or a triple bond. Start by drawing in your bonds as lines, and then add your lone pair electrons around each atom. So let's do a couple of examples to help you see how this works. So we're going to start with good old water, H2O. So we have hydrogen, and we know that it has one valence electron, and then oxygen, which has 6 valence electrons. So if we quickly draw our Lewis structure for that, I'm just going to draw this like this to start off with, and then we have another hydrogen, so I'm going to put another hydrogen over here. So if you look at the way I have this set up, you can see there's a place on two sides of the oxygen and the hydrogen where you only have one electron. And so this could be a bond forming here. These two electrons can make a bond, and these two electrons can come together to make a bonding pair. And that is going to then give oxygen the 6 electrons that it had present to begin with, plus these other 2 electrons that hydrogen originally brought into the relationship. So oxygen has 8 electrons. It has access to 8 electrons. It has all of those 8 valence electrons that the bond is supposed to provide. So the oxygen is happy. Hydrogen, like helium, only needs 2 valence electrons, and so it has the one that it started off with, and then it's going to borrow this one from oxygen to make up the second one that it wants. So the oxygen has access to 8 electrons. The hydrogens both have access to 2 electrons. Everybody's happy. We have a good molecule, a covalent molecule of H2O. How about NH3, ammonia? What do we have there? Again, hydrogen only has 1. Then we have nitrogen. Nitrogen is in the 5th column of when we label things to think about valence electrons. And so it's going to have 5 electrons around it to begin with. We have 3 hydrogens present, so I'm just going to draw another hydrogen over here with its 1 electron, and I'm going to draw another hydrogen over here with its 1 electron. So remember, even though I typically start the Lewis dot diagrams on the right, you really don't have to. You can put those electron dots anywhere around the atomic symbol. And so here I've oriented them quite nicely so you can see that we can make a bond here between these 2 single electrons, and a bond here between these 2 single electrons, and one more between these 2 single electrons. And so that leaves us with nitrogen having the 2 electrons it came with. This is one of those lone pairs, only belongs to nitrogen, plus 2 more over here in this bond, 2 over here, and 2 over here. So nitrogen now has 8 electrons. It's happy. It has its octet. And each hydrogen has 2 electrons for itself, and the hydrogen is happy. So that's how nitrogen and hydrogen bond together to make ammonia. And if we drew it out as a Lewis structure that was maybe a little bit neater than what we see right here, you would just do the lines to the hydrogens coming out from your nitrogen, and then the 2 electrons that are the lone pair here above the nitrogen. So this is your Lewis structure for ammonia. How about Ch4 Methane? So again, carbon is going to have 4 valence electrons, and so you can see there's 4 different directions that carbon is going to want to bond to something. Hopefully by now you can think, oh, we could put this hydrogen, kind of one on each corner of the compass here with its single valence electron, and that's going to give me a place where I can put in a bond here, and a bond here, and a bond here, and a bond here. Then carbon has access to its 8 electrons, and it's happy because each one of these is going to be on 2 electrons in each place, 2, 4, 6, 8, and each hydrogen again has 2 electrons, and so we have all of these are single covalent bonds holding these covalent molecules together with shared electrons, electron pairs, bonding pairs, where you have 1 electron provided by each of the 2 atoms involved in the bond. Now remember, covalent bonds can be multiple, they can be double or triple bonds. So how does that work? Well, here again we've got carbon and oxygen, 2 elements we've already worked with. Carbon is going to come with 4 valence electrons, and then oxygen is going to come with 6. And so this one is it's going to be a little bit trickier. I'm going to put my 2 and 2 over here. So I'm going to draw my oxygen like this on this side, and on the other side I'm going to draw my oxygen like this, just for the purposes of doing this diagram. So there's my oxygen with 6. So take a look at this. Where do we have 1 single electron looking to bond with somebody else? Well, these are very obvious right here between the carbon and the oxygen, but we also have a carbon and oxygen bond that could happen here and one that could happen there. So this is an example where a double bond forms. So if we were going to write this out in a little bit neater form, we'd have carbon double bonding to oxygen. There are no lone pairs on carbon, but we do have 2 lone pairs that we need to show over here on our oxygen. So this is our Lewis structure for carbon dioxide, showing the double bonds of carbon here present as 2 lines. Let's look at our second example here with the formula C2H4. This actually has its own name again. This is ethylene, one of those compounds that kind of falls in the organic chemistry area where it has a more distinct name. But we've got carbon, good old carbon with its 4 valence electrons, and we have 2 carbons with each of them having 4 valence electrons, and then we have 4 hydrogens. So we're going to have a hydrogen over here, and a hydrogen over here, and another hydrogen over here on the left, and I'll just put one more down here on the bottom. So I'm kind of deliberately lining these up so that you can see that we can make a bond between a carbon and a hydrogen in each one of these places, and that leaves our each individual carbon molecule with 2 unbonded electrons, and so they can form a double bond to hold those carbons together. So if I was going to draw the molecule in my kind of crowded space over here, we would have carbon double bonded to carbon, and then we would have hydrogen going off on the other side of each carbon. So that's showing you a double bond forming between molecules. Again, just looking to see what valence electrons are present, making bonds between 1 on one atom and 1 single electron on the other. And then finally, triple bond, 2 common examples of that. So we've got N2, nitrogen gas. 70% of the atmosphere, more than 70% of the atmosphere is nitrogen gas. You're breathing it in and out all the time. So nitrogen we have drawn already. It has 5 electrons. So I'm going to just put the lone pair off on the left, and we have this other nitrogen that also has 5 valence electrons. And so again, you can see here are 3 places where 1 electron on one atom can bond with 1 electron on the other atom, and we're going to end up with a triple bond. And again, that would be drawn with 3 lines between your 2 atomic symbols, and then draw your lone pairs on the other side. And then finally, C2H2, another compound that has its own name, and we want to show our carbon with its 4 valence electrons. We have 2 of them. And then we've just got an extra hydrogen, and of course we're kind of distributing them equally, 1 on each side. Again, to make your bonds, the carbon can bond to each hydrogen, and then we've got 3 bonds for carbon. A triple bond is the biggest bond carbon can make to itself, so it can't make a quadruple bond to itself. Triple bonds are as big as you get in covalent compounds. So there you go. You're going to have a chance to practice this in covalent compounds with Lewis structures. Just a few more words. When you have a strong bond. It holds the molecule together well so that more energy is needed to break it. And so covalent bonds in general are much stronger than ionic bonds, though the exact amount of energy needed to break that bond is going to vary depending upon what atoms are involved. And if you have multiple covalent bonds, such as double or triple bonds, they are even stronger. So covalent molecules in general hold together better than ionic molecules, and you are basically made of covalent molecules, and it's a good thing because we want to make sure you all stay together. So this finishes my overview of the covalent bond and how you use the Lewis structure to illustrate what the molecules look like.